differential equation I'm dealing with will be a second order linear differential equation. The process is called reduction of order. So I want to get my equation in the form y double prime plus p of x y prime plus q of x y equal to r of x. Well, it might come in the form a sub 2 of x y double prime plus a sub 1 of x y prime plus a sub 0 of x y equal to g of x. So all you have to do is divide each term by a sub 2 of x, and you'll get it in the form y double prime plus p of xy plus q of xy equal to r of x. The reason that we want this form is that we're given a solution y sub 1 of x, and our purpose is to find a y sub 2 of x, and that's how we reduce the given equation to a first order linear differential equation. It turns out that our y sub 2 given our y sub 1 as a solution will be y sub 1 times the integral of e to the negative integral of p dx divided by y1 squared. And it turns out, for those of you who like contemplation and theoretical formulation, that e to the negative integral of p dx is really the Wronskian of y1, y2. Okay? So let's just take an example to see how we apply this. Suppose we wanted to solve x squared y double prime minus xy prime plus 2y equal to 0. And we're given one solution, namely that y sub 1 is equal to x sine natural log of x. So it turns out then that my y double prime minus 1 over xy plus 2 over x squared y equal to 0 is the reformulation of the problem. All I did was divide each term by x squared. So, based upon the given formula, y sub 2 equal to y sub 1 integral of e to the negative p dx y sub 1 squared, where my p of x now is negative 1 over x. I'm going to get y sub 2 is equal to x sine ln of x, the integral indefinite of e to the negative integral of 1 over x dx divided by x sine ln of x squared. Okay? Well, y sub 2 then is equal to x sine ln of x integral of x dx divided by x squared sine squared ln of x. Well, where did the x come from? Because e to the negative integral of negative 1 over x dx is e to the ln of x, and e to the ln of x in the integrand is just x. And that's where we drop down from to see that our y sub 2 now has to take this form. Well, now we can do some substitution by letting u equal to ln of x. Du is going to be 1 over x dx. We got all these characters here in my equation. You look at it. Cool. So now I have x sine of ln of x, negative x, well I have x sine of ln of x du divided by sine squared of u. And it's going to be equal to x sine ln of x cosecant squared of u du. And of course the antiderivative of cosecant squared is negative cotangent of u. So I got negative x sine ln of x cotangent of u plus c, since it's a definite integral. But the cotangent, my u first of all was ln of x for my substitution. So now if I substitute that in negative x sine ln of x cotangent of u plus c, it becomes negative sine ln of x cosine of ln of x divided by sine of ln of x plus c. And this is equal to negative cosine ln of x minus a constant c times x sine ln of x. But my general solution is the sum of those two solutions, y1 and y2. It turns out to be negative cosine ln of x minus cx sine ln of x. Voila! This is a beautiful thing. There's a lot of manipulation that goes on in solving this, but you can get to it step by step if you were a diligent student in Calculus 2. I'm just pointing out all the fascinating integration techniques that helped us to derive our solution. So try reduction of order differential equation. Second order of the form y double prime plus p of x y prime plus q of x y equal to some function of x. Using this methodology, given a solution y1, to get your solution y sub 2, and you will become a master of doing second order linear differential equation. Voila!